All right, so we had our method erased. So kind of what we want to think about, we have this reference command that we're able to choose as a controls engineer, as a controls designer. And we want to think about, well, how should I choose that reference command? To do that, let's back up a little bit. I'm going to take some flexible system, some system that can vibrate. And what I'm going to say is, well, I can hit this system with an impulse. An impulse, right? Hitting the system, right? I have some flexible system, and I hit it with an impulse. What's going to happen to it? What does it do? It's going to start moving. How's it going to move? You actually can hear it. What does that sound? The sound is just vibration, right? So we have some A1, so we have some kind of impulse A1, and then we can have some kind of response to that impulse. Some vibration back and forth. Okay. If I took that same system and I hit it with another impulse a little bit later, what's it going to do? Well, forget about the first one. What's it going to do just the second one? Just a second impulse. Let's say, maybe it's here. I hit it with an impulse later. It's going to create some vibration too. Okay? So I win an impulse, and it creates some vibration. If I hit it sometime later with an impulse, it's going to create some vibration too. Right? Well, if I pick how hard I hit it, which is the size of A1 or A2, and I pick the timing of when I hit the system for A1 and A2, then maybe what's going to happen when those two add together? As I've drawn it here, what happens after A2? Yeah, so those two guys add together. And then what I get, after A2, you see A2 response and A1 response are canceling each other out. Total response. What property has to hold for this to be true about your system? Yeah, so I have to pick A1 and A2 the right way, the right sizes and the right timing. Okay? But even if I've picked those kind of correctly, there's something else that is happening here, has to be true about my system for this to work. If my system changes in some way between A1 and A2 during this time, will this work? No. Right? If my system happened to respond differently to A1 than it did to A2 than it did to A1, will this work? No. So if the system's not changing and its response is kind of constant, proportionally wise, let's say, what can we say about our system? Is it linear or nonlinear? Well, what we said is that kind of the response is not changing over time. Is what I mean by kind of constant properties of the response. So we don't have a system that's changing with time, and we have a system response that is not different based on time or system state. It's linear, right? So this requires system linearity because this relies on superposition. Right? Superposition is what makes this work. Right? And superposition only strictly holds for linear systems. Right? It can kind of almost be true for nonlinear systems. All right, but strictly true only for linear systems. So this is kind of a cool idea. If I have these impulses and I hit on my system at the right time, I can get no vibration still. Well, what kind of system do I drive around by smashing into it and hitting it? Is that how you control systems? You have some robotic arm that's moving around. Do you go up and smash on it to make it move? I think no, unless you guys do something really different here in Korea than I think. Right? We're not we're not hitting the system to tell it to move. Right? So we need to do something other than impulses. These impulses are effectively just hitting the system, right? Well, luckily what we can do is if we take this impulse sequence and we've designed it properly, we can actually take that sequence. Actually, let me draw these in colors too. You can take A1 and A2, and let's say A2 happens at time delta. Okay. And so I kind of had this idea that I think might work. Right? And I could take these two impulses and write them this way. And maybe I'm going to say, hey, well, make sure you do that impulse A1 at time 0. And what I want is to construct some kind of continuous command with this. So I'm not just hitting my system with the impulses themselves. Well, maybe, let's just try a command out. I want to move my system 1 unit. Okay. So my original reference command let's say unshaped, kind of preview what we're talking about. My unshaped reference command is just a step, 1 unit step. Okay. What kind of response? If my system is flexible, what kind of response does this create? There's going to be some vibration, right? So we can draw that up too. Let's see, we'll draw dashes. So I have some system that's flexible. I give it a step command, it's going to start vibrating in some way. And maybe not quite that much, but whatever. Well, what I'm going to do is I'm going to do this operation called convolution. And I'm going to take my original unshaped reference command and convolve it with this series of impulses. What this does for us is take the frequency domain, the characteristics of this impulse sequence, and transfer them over to the result of this convolution. Okay, and there's a lot of different ways we can think about it, and we'll get to some of those soon. This convolution operator for an impulse sequence is really, really easy to do, actually. So let's look at what the resulting command is going to be. Okay. So to do this convolution, all I need to do is take my original unshaped reference command, this step, and multiply it by A1, and do that at the time of the command plus 0. Okay. So for A1, part of the command, we end up, instead of a maximum of 1, we get a maximum of 1 times A1. And that just starts at time 0. Okay. So that's the first part of my command. I take and multiply by A1 and do that at time, an offset of time 0. Okay. The second part is I take my original unshaped reference command and multiply by A2 and do that at time delta. Okay. So I'm going to space over for delta. And I just have a smaller step now. All right. So the A2 part. And then the third step of this process is just to add together those two pieces. Okay? So in this case, I have the first step. So from there, it's only A1. And I get here, I just have to add the second piece on, which should be to there. Okay. So now I have the total command. And if I've designed this correctly, if I've picked those impulses where this works, then the response I get is quite nice. It's something like that. It's not quite right, but there's a nice pretty picture in the notes. Okay. So all that depends on me just picking out these impulses in the right way. In this convolution, the process of that works. Even if you have 15 impulses, that process is the same thing. Okay? How you actually do that convolution process. Okay. What we're going to say is that this series of impulses we've designed in this way. It's called an input shaper. And it's called an input shaper because it changes the shape of our input, basically. It's picking out the shape of our input for us. And hopefully we picked it out in a way that's going to create low vibration. Okay, so this is kind of an intuitive understanding of how this might work. Let's talk for just a minute about the math behind why this works. Okay. If I look at the vibration from a series of impulses, we get the vibration from a series of impulses. We're going to call it the kind of summation, or summation over the n impulses. We're going to end up with forgot a term about that. Sorry, let me fix that for you. Sorry about that. So again, I take a series of n different impulses. And if I know how big each one of those is, AI, in the time that it happened, Ti, this equation is going to represent the vibration that results from those impulses. Okay? Well, that's going to change a lot based on what my system is. So I'd like some way to be able to normalize this value. So we want to normalize it. So what we can do is take just one impulse of unity magnitude. So and look at what would be the vibration from that. Just hitting it once with some kind of unity magnitude. Well, if we plug all that into the equation, ends up being just that. Okay? So what we can do is take and divide our impulse sequence from n different impulses and divide it by what happens if it's just one impulse at time 0. Okay? And really what that does for us is change this equation to be just vibration and gets rid of that part of it. So you'll see that written that way. Where this vibration equation is a function of the natural frequency omega and the damping ratio of the system zeta. So now we have an equation that, given some kind of impulse sequence, if you give me AI, a bunch of A's, a bunch of impulses, and their times, I can predict for you what the vibration that would result from those impulses is. Right, using this equation. Everybody following so far? Okay. Well, if I have that equation, well, that probably gives me some information for how I can design, how I can maybe pick those impulses. Okay? So I can set some constraint on vibration just by setting that equation less than some tolerable level of vibration. So I have this equation that would predict how much vibration results. I can say, well, hey, I want that vibration to be really small. And I can create some kind of constraint equation that says make this, pick an A1, or pick A's and T's, such that my vibration is less than some tolerable level. I want it to be tiny. Okay? So I have kind of the first constraint in my formulation of how to solve for these shapers. So let's kind of box that. So we'll save that one. Okay. And that's the constraint that's going to give us the low vibration. How many different choices of AI and TI would give us, or can give us, low vibration? And actually the same would be true. Even if we limit vibration all the way to 0, how many choices of AI and TI do we have to make that 0? Well, let's think about that, okay? So I'm going to say, let's make a new impulse over here. Let's call it A2 bar, maybe. What's another place where I could place an impulse on this original diagram that would result in 0 vibration after the 2 impulses are finished? So I placed one here. Where else could I put one? The next cycle, yeah. Right? So I could put one And it's actually going to have to be a little bit smaller. But I could put A2 bar there, and it would create some vibration. Right? And then you still get to low vibration. These two add together to give it 0 still. Right? And I could wait till the next cycle, and the next cycle, and the next cycle. So even for this really simple case, there's actually infinitely many solutions if I just want to limit the vibration. Right? A1, there's infinitely many choices of A's and T's that would give me low vibration. So I have to further constrain my problem in some way to get a solution. Okay? And this actually is, if you kind of work on this input shaping stuff longer, this idea is one that turns out to be really useful if you're working with some complex system, because there's infinitely many solutions. So even in our simple example, I have a choice now. I could have A2 bar. I could wait until out here. Maybe there's some kind of A2 prime. Right? Which solution of these kind of three should I pick? The first one, why? Quickly as possible, right? So we know, in this case, A2 is the kind of first, is the earliest we can have no vibration. Well, that's generally what we want. We want our system to move as fast as possible, but still not vibrate when it's finished. So we can kind of constrain. So we can take, I want to write this. So of all these infinitely many possible solutions, we want the time of the last impulse, Tn, to be as low as possible. Well, in terms of the solution, we just say, well, I want the minimum Tn. And if you're thinking about this from a kind of numerical solution perspective, that's my actually objective function. All right, so I have a constraint. On vibration amplitude after my series of n impulses. I'm going to have some objective function. So I hit the mat. My objective is to minimize time Tn subject to some vibration constraint. Okay? So just with these two pieces of the puzzle, these two pieces of solution, what's going to happen? Do we need other constraints? In other words, to get to a feasible solution, a real solution. We have to know some information. So certainly, to solve this problem, we need to know the natural frequency and damping ratio of our system, for sure. Well, let's look back at what happened here. And I kind of made some assumptions in this problem and didn't kind of clue you in on them yet. Right? In order for my shaped command, the total response in black here, to get to the same position as the original unshaped command, what has to be true of A1 and A2? Okay. So in order for my shaped command, the black one over here, the staircase one, to get to the same final position, 1, as the unshaped command, which got to 1 as well, what has to be true of how big A1 and A2 are? Should be 1, right. So she said A1 plus A2 need to be 1. Right? Because remember, they're just kind of adding together to get to the total command. Right? So we also need we're going to have a constraint. We have a constraint on the sum of my impulses. If I add up all the impulses in my sequence, in this case it was only 2, they better add to 1. And what that's going to do for me is make sure that I get to the same final place as the unshaped original command that I'm doing this input shaping process on. Okay. What kind of solutions would I get now? What else do I need to include? So if I'm trying to minimize the time, I've said that these things can sum to 1, but I haven't said anything about their absolute amplitude, right? So I could have plus infinity and minus infinity. And plus infinity and minus infinity. I'll be pushing and pulling and hammering everywhere, right? And yeah, I could get some solution for that works mathematically and satisfies these constraints, but it's not one that my system can actually do. So I also need to set some bounds on the amplitude of the impulses. Right? So in this case, I'm going to say for all AI greater than 0. Or to say it another way, just to write it out. I have some constraint on the amplitude of my impulses. In this case, I'm going to say for all my impulses AI has to be greater than 0. Okay? All the impulses have to be positive. That's where we're going to start. We can relax this a little bit later, but let's start there. Okay. So with this set of constraints, I have basically 1, 2, 3 kind of theoretical constraints, let's say. I'm going to limit vibration less than V tall, less than the tolerable. I want vibration to be really small. I want all my impulses to add together to be 1. And I want all my impulses to be positive. Okay? That's a pretty good set. So if I where can we go now? Let's go all the way over here to the left again. Okay. Let's look at a solution. And let's pick a kind of easy solution. For now, I want I'm going to say I want vibration to be 0. Absolutely 0 when I finish this. Okay. Well, so that means that kind of V or equal to 0. Okay. So V tall is equal to 0. I still have these impulse amplitude constraints. So my full solution set, summation all my impulses sum to 1. I have impulse amplitudes greater than that. So basically I want to pick the minimum time subject to fulfilling those constraints. So we can solve this numerical optimization. Right? In this case, for the simple case, we actually can solve it in closed form. which is quite nice. Okay. So I can solve this out, and actually in the notes, there's all the intermediate steps for the solution. We'll skip just the math for here. And what we'll find is because we said, hey, I want vibration to be 0, we call this a zero vibration, or ZV, input shaper. Okay. Okay. And the solution looks like this. So we're going to say ZV and we're going to write it in this form where the top row is the impulse amplitudes and the second row is the time at which they occur. Never remember that. Where K is that? In TD, tau D, is the damped period of the system. Okay. So we know for this set of constraints, we get this zero vibration shaper, and that is its form. Okay, we know this in closed form. It's quite nice. And that's kind of the case we've been looking at so far. These two impulses. Right. So another way we can write this shaper is this. We're going to draw this shaper. Let's look at the two impulses have that kind of form. Okay. Again, it's ZV input shaper, zero vibration. So we've said so far that we need to know our natural frequency and damping ratio in order for this to work. Our solution, right, embedded in that vibration equation are knowing the natural frequency and damping ratio for all of these different pieces. Okay. Are we ever going to know either of those things exactly? Natural frequency and damping ratio. Are we ever going to know it exactly? Exactly right, no error at all. There might be some error. I'm going to tell you there's always some error. You're never going to get the natural frequency and damping ratio exactly right. Right? We can get very, very close quite often, but there's always going to be some error. Right? Any model, any simulation model you're creating in your entire life is going to be wrong. Just by nature, it is wrong. It's just up to us as engineers to decide, is it wrong enough to where it won't work for what I need? Okay? So we know our natural frequency, we can measure it, and we know with some confidence maybe it's right, but it's still not going to be perfect. And we realize that, then we also need to look at this problem and think about, well, what happens to our solution? We design this ZV shaper for some natural frequency and damping ratio, and we know it's going to be wrong. How does that affect how this performs? Let's look at that. So let's take a look. Let's see, we'll erase, we'll leave that part up. We'll leave our solution up, the ZV shaper, and we'll squeeze in the middle here. Okay. So I'm going to plot what we call a sensitivity curve. On the horizontal axis, we're going to have a normalized frequency. And what that really is kind of the actual natural frequency. I'm calling it kind of omega act or omega actual, divided by what we modeled it as. So we thought the natural frequency was 1, and it's actually 1.2 or something. Or we thought the natural frequency was 1, it's actually 0.9737, whatever. So this gives us a normalized version of what the natural frequency is. So if I move at 1, which I've drawn here, my model natural frequency exactly matches the actual natural frequency. There's no error. So if we look at this curve, the horizontal or the vertical axis of this, the y-axis of this plot, is basically just this equation. How much vibration results from that impulse sequence? Okay? So if we design our ZV shaper exactly right, and our frequency exactly matches what we modeled it for, how much vibration does this create? 0. Exactly right. So at 1 on this plot, I have 0 vibration. Okay? As my natural frequency starts to deviate from what I modeled and designed the ZV shaper for, what happens to the vibration?
There will be some.
It's going to be some vibration, right? If I think about the impulses I had up here, my impulse is now going to be at the wrong time or the wrong size. So the two curves are not going to cancel out anymore. Okay? So I get some curve. Let's see. That actually looks like that for a ZV shaper. And let me draw some bounds on this. Let's see. Well, that's okay. Okay. If we look at this, we can get some measure of how well this ZV shaper responds to error in our natural frequency by looking at how much this curve changes as a function of that frequency. How quickly does it get to be too much vibration, basically? Okay. To do that, we're going to set some value, let's say we're going to pick some value to measure the kind of performance of the shaper. In this case, we're going to say 5%. What that 5% means is that at 5% here, the vibration is 95% less than it would have been without input shaping. So vibration has been reduced 95%. Okay. So what we can do for these input shapers is look at how much of the curve and let's see, write it up. This plot is called a sensitivity curve, or sensitivity plot. We call these for input shapers. It tells you how sensitive the shaper is to changes in natural frequency. And we can take this sensitivity curve, or the sensitivity plot for the ZV shaper, and look at how much of the curve, how much of it is below my tolerable level of vibration. Okay. And we can look at the width right there. And for the ZV shaper, that's 0.06. So the width of this curve for the ZV shaper is about 0.03 above and 0.03 below. What that really means is that we have less than 3% error in our natural frequency, I'm able to reduce vibration by 95% or more. Okay. So that sounds kind of hard to hit. What's nice though is even out here, like what I've shown is about to say kind of 1.2, 0.8, And this over here is still only about 30%. Right? So even if I'm off by 20%, I'm still reducing vibration by 70% of what it would have been without input shaping. So I think kind of to keep in mind that this is still a pretty good result. Even if I have 20% error with the ZV shaper, I'm still reducing vibration from what I would have had without it, which is a really, really positive result. Okay. That said, would we like to be less sensitive to error or changes in natural frequencies? Would you like this curve to be wider? Yeah, we would. Right. This works really, really well, even this really simple solution. Right. But yeah, it would be better. We want it to be 0 all the time if we can. So we don't have to estimate natural frequency really well at all. It's going to be 0. Oh, that can't quite get there. But what we can do is get to another kind of input shaper called the ZV shaper. Two-thirds of the way up. We're going to look at the sensitivity curve. This next shaper we're going to talk about is called the ZVD. And it's zero vibration and derivative input shaper. And what the ZVD shaper does is take the same constraints as the ZV and add one that the derivative of the vibration equation with respect to natural frequency is 0. So this is the ZVD constraints. So we add that to our set of constraints that we had for the ZV shaper. So we're still going to set vibration to 0. If we add that derivative constraint in now we have what's called a zero vibration and derivative shaper, a ZVD shaper. Okay. And it has the form. Make sure I'm getting this right. That's 2. So there's our solution to the ZVD shaper. And we know this one in closed form too. And the K here is the same K we had over there. So that's our ZVD shaper. What do you notice about the ZVD shaper compared to the ZV? It has one more impulse. Okay. What else? Yeah, it's longer as well. If we look at the duration of the shaper, what's the time of the last impulse? This one is tau d over 2, so half a period of oscillation. Look at the ZVD shaper, it's 3 impulses now, and that may be not such a big deal. The biggest change is that the time of that last impulse is now a full period of oscillation. Okay. And what that does for us is that this is how much the command, remember we had that step This is how much the command duration is increased by the shaper. So the longer this time is, the slower your command is going to be, basically. Slower your response is going to be. So we want this, well, we want it to be as little small as possible. And in this case, to satisfy the ZVD constraints, it has to be longer than it did for the ZV. And that should make some intuitive sense just from a kind of pure mathematics perspective. We have a problem, we added some constraints on it, we're going to need a longer solution. We need more degrees of freedom to be able to get to a solution. So in that case, we have 3 impulses. If we look at the ZVD shaper, its width for under VTOL is 0.29. So kind of plus or minus 14.5% around the design frequency, we get less than 5% vibration we would have had. Okay. These parameters we call that insensitivity. So the insensitivity of the ZV shaper is 0.06. The insensitivity of the ZVD shaper is 0.29. Okay. Let's look at one more of these kind of shapers. We've said so far that no matter what we do, how good our measurement of some system is, there's going to be some error in natural frequency, some kind of error in damping ratio, in our estimate of it. Right? So what that's going to mean is that we're always going to be a little bit wrong here. We're never going to be able to get exactly 0, except by mistake, basically, or by luck. So if we think about that constraint, if we think about the constraint over here that we're trying to get 0, it doesn't really make any sense. Because we're never going to be able to get 0 because we're never getting natural frequency or damping ratio correct. Right? There's always going to be some error. We're never going to be at 1 unless we get lucky. Never going to be at 1 because we're going to always be a little bit off. So if you think about that, well, maybe there's something to be gained in our solution procedure for not trying to get 0 anymore. If we kind of realize we're never going to be able to get it anyway. So maybe let's say, let's actually relax it away from 0. Let's add the design frequency, let's let it maybe be instead of setting it to 0, let's set it to 5%. So at our design frequency, I know it's going to be wrong a little bit. Just let it to be 5%. Okay? And what that does for us is actually something like this. Turns out to be pretty cool. If I relax that constraint at the natural frequency, so I'm not trying to get 0 anymore, that creates this curve now. And that's an EI shaper, an extra insensitive shaper. And really the whole key to that solution is just realizing I'm always going to get my frequency wrong. I'm always going to get my damping wrong. So I shouldn't try to have 0 vibration. Now I'm going to flash up. We'll look in just a minute. This EI shaper actually gives an insensitivity of almost 0.4. It's actually 0.3992. So almost plus or minus 20%. We can keep it below 5% of what it would have had without input shaping. That's quite a nice result. I think we're never going to be able to get a natural frequency exactly. I think most times you're going to be able to get it within 20%. So if we're able to use this input shaper, able to use the ZV, I still can get really low vibration and do pretty well. Right. I can get within that 20% of natural frequency. Okay. So there's the three most common, what we call positive input shapers. ZV, ZVD, and EI. And they're called positive impulse shapers because we were forcing the impulse amplitude to be positive. Okay? So let's take a 5-minute break this time. Just 5 minutes. Then we'll come back and I have some slides to show you of how this input shaping works in practice. Okay? So come back at 12:20 or just relax for a minute while I get the slides ready. All right.